Hello everyone. I'd like to start my presentation titled Effortlessly Build High Performance AI/ML Processing Pipeline within the ML Lifecycles. Okay. Let me briefly introduce myself. I'm Yamamoto. I'm the researcher at the NTT Corporation in Japan. My research area is distributed systems and virtualization. And I'm currently working on data-centric infrastructure, which is promoted by IBM Global Forum. In short, my research focuses on controller software for ICT infrastructures. And today's presentation is also part of that work. Here's today's agenda. First, I'll explain the introduction and the POC. Next, I'll show you a demonstration. And finally, I'll talk about our future work. Now let's move on to the introduction. Let's start with the current issue and requirement faced by ICT infrastructures. We're seeing advances in sensing, networking, and AI technologies, and they are driving the demand for real-time AI processing in ICT infrastructures. The amount of data in these infrastructures keeps growing, and we process more and more data. The power consumption keeps increasing. Therefore, both high performance and power efficiency are now required in ICT infrastructures. Let's take a look at current execution model. So we believe that the performance per power consumption is still insufficient. Compared with the accelerators, the CPU provides lower performance per power consumption. Yet, it still has many tasks, such as pre-processing and post-processing. At the same time, power-efficient accelerators are mainly used only for specific tasks, such as inference. Therefore, we see a room for performance improvement in the parts that are still processed by the CPU. To improve performance, we propose an execution model called the processing pipeline. In this model, each task uses the most suitable accelerator, so the processing pipeline can achieve high performance per power consumption. The reason behind this proposal is the recent emergence of accelerators, such as TPU and TPU, and so on. Based on this, we believe that tasks executed on CPUs will be shifted to more specialized hardware. However, this also raises an important question. Since the processing pipeline uses multiple and heterogeneous accelerators, users might wonder if using multiple accelerators seems challenging. They may also worry that this approach could increase development cost or reduce usability. But don't worry. The concept of processing pipeline is rooted in data-centric approach. In other words, application-side users can focus only on the processing they want to perform and think of their applications as data flow. Eventually, users will not need to care how the processing pipeline is actually deployed inside the ICT infrastructures. Based on this concept, the main topic of today's session is introducing a method to deploy a processing pipeline that is rooted in data-centric approach through our POC. In the next part, I will explain how to deploy a processing pipeline effortlessly, and in the demo part, I will show you how to update the structure of a processing pipeline. Before moving on, let me add one more note about our POC. The POC is a step toward realizing the concept. As I mentioned earlier, the processing pipeline assigns the most suitable accelerator for each task. However, in this POC, we are using GPU only for inference. But technically, it is also possible to assign the GPU to the filter size. So this limitation doesn't affect the purpose or validity of our demonstration. Now, I'd like to explain how to deploy a processing pipeline effortlessly. In this POC, we built a video inference system as an example. The users simply writes a manifest that describes the structure of the processing pipeline. And by deploying it via Numaflow on Kubernetes, the entire pipeline can be easily deployed. In this pipeline, the input component accesses an external video streaming server and receives a video stream. Each frame is processed by the filter size and the inference component. Finally, the processed frames are sent to an external video display server. This book has two key points. The first one is Numaflow. It's an open source software it's open source software that provides a Kubernetes native and serverless platform. It is mainly developed by Intuit Convention and has been presented several times at KubeCon and Cloud Native Con. The second point is dynamic resource allocation. So it's a Kubernetes feature used to assign resources such as hardware accelerators to pods. This feature became stable in Kubernetes version 1.34. Let's look at the Numaflow itself. First, one of the key points of Numaflow is visibility and control. It allows us to easily define and visualize the structure of a processing pipeline. Let's look at the manifest. First, the user defines a component called vertex within the pipeline manifest. In this example, we define 4 components: input, filter size, inference, and output. Then, users also define the connectivity of them. By simply deploying this manifest, we can automatically deploy a processing pipeline with this structure. And although we didn't use it yet, so Numaflow itself already supports data flow, diverging, and converging. Next, let me move on to the second key point. It's developer friendliness. Users can operate Numaflow just like using Kubernetes. This is because each component of Numaflow is defined by custom resource definition. When the pipeline is deployed, each controller sequentially starts creating the corresponding resources. As a result, the vertex and the pod resources are eventually created. Therefore, the DLE field is included in the pipeline to allocate GPUs. It can finally be processed as a pod level field. To summarize so far, the processing pipeline is an execution model proposed for performance and power efficiency, rooted in a data-centric approach. We have shown the method to deploy a processing pipeline effortlessly using Numaflow. Okay, next let's move on to the demo. In this part, I'd like to show you how to update the structure of a processing pipeline. In the first example, we focus on updating the accelerator through building a video inference system. Specifically, imagine you first use a low-end GPU such as T4, but you find that its performance is insufficient. In that case, you can simply modify a part of the manifest to switch to a high-end GPU like a A100. Okay, let's move on to the video. Okay. First, let me explain the demo environment. The processing pipeline will be deployed on Kubernetes cluster, and on the lower side of the screen, so you can see the control plane. And there are 2 data planes on top of the screen. Okay. The left side, it's control plane, so this is data plane. So this data plane is equipped with A100 GPU, okay, while the second one has a T4 GPU. So sorry, the character is lower than I expected. So, okay. At this point, so no pipeline has been deployed yet, okay? It's clear status, okay. let's start the video display server and the streaming server. Okay, now deploying. Okay, the both servers are launched. Okay, and the two processes, so around where the cursor is moving, are the ones. Yeah, so both servers are now up and running. Okay, now let's check the input video. Okay, yeah. So this screen shows the desktop of the control plane, which is running in a remote environment. So and the input video stream will be playing here. Since this is a 4K video stream, there's a slight delay between the remote environment and the local environment where the video is being recorded. So, yeah. So please note that some lag is expected here. Okay. Oh. So 4K is very heavy, very heavy. Yeah. But here's what the input video looks like. Yeah. Please remember. Okay. So, all right. Okay. Yeah. Let me now, explain the first pipeline. Okay. Okay. As shown here, so the pipeline is named Kubeflow NADM1. Okay. So within the pipeline, so we first have input vertex. Okay. This is the input vertex. Okay. Okay. Next, so filter size vertex is defined. Then, so inference vertex is defined, and so this uses the T4 GPU in this case. It's important. After that, we have output vertex. Okay, and finally, the edges, so its connectivity, are defined to describe the connectivity among these vertices. Okay. Now let's deploy the first pipeline. Okay, the pipeline is deployed, and the corresponding pod is also created. Okay, so I'm sorry to character is so over. Yeah, but so their pod's name starts with Kubeflow and a demo. Okay. Now the pipeline is up and running. Let's check the output video. Okay. Here's input video. Input video is processed through the pipeline, and the inference results, the bounding boxes, are overlaid on the video. Okay. Next, let's check which GPU is actually being used. Okay. First, let's check A100. Yeah. So as you can see, it's not being used right now. So percentage is 0. So it's not used. And so let's check T4. Yeah. T4 is running. So 35%. Yeah. So it's clear that the inference processing is using the T4. Okay. Next, I'll explain the second pipeline. Okay. The pipeline name remains the same. The only change is that the GPU used for inference is switched to A100. Okay. Now let's deploy the second pipeline. Okay. Wait. Yeah. Okay. Please wait. It's video. Yeah. Okay. As the pipeline is being switched, the video stream temporarily stops. Yeah, and once the deployment is completed, the processed video starts playing again. Okay, start again. So visually, there's no difference, but you can confirm, okay, that the redeployment has been completed. Okay. Okay, next let's check that A100 is now being used. Okay. Okay. As you can see, A100 is running this time. It's at 8%, not 0%. Okay. On the other hand, the T4 is not used, so 0%. Yeah. Okay. Through this demo, I hope you can see how easily the accelerators used in pipeline can be changed. Okay. Okay. Now let's return to the presentation and I'll explain the second demo. Yeah. In the second demo, we'll update the inference model through the integration with Kubeflow. By running a Kubeflow pipeline, we can register a trained model into the Kubeflow model registry. Then, when building the content image, the updated model is pulled from the registry. We'll change the inference model from ULV4 to ULV7 to indicate model update this time. And then we deploy the new pipeline using Numaflow. Okay. And for this demo, we'll start from where we deploy the second pipeline from the previous demo, but with a different name. So, and the stream and display server have started, and the steps up to the container build are omitted in demo movie. Okay. So in this demo, we won't be using the T4, so I'll hide that window. Okay, next I'll explain the third pipeline. Okay, the pipeline name remains the same as the second one. It's Kubecon and demo 2. Yeah, it's the same. The difference from the previous pipeline is that a different inference model is used. So it's ULV7. Okay. So let's deploy the third pipeline now. From now. Okay. Okay. Once the deployment is completed, you'll see multiple bounding boxes displayed in the bottom right window. Please note that this behavior is not due to the model itself, but it's intentionally set for the purpose of this bug. Okay. Now the redeployment. Okay. Okay. As you can see now, so multiple bounding boxes are shown. This indicates that the pipeline is running with ULV7. Okay. Okay. Visual stream is here. Okay. Okay. So let's look at the performance result. Please focus on the top left and the top right of the graph. So from the first to top left, yeah. The input video is running at 15 FPS, okay? And you can see that the processing performance is also around 15 FPS, okay? Moving cursor, okay, here. Okay, so the system is keeping up with the input rate, okay? So through these two demos, we can check the performance easily, and we can also switch accelerators and models and then redeploy the pipeline. It's very easy. Okay. So this demo has already been available on GitHub. So I hope you can easily try it out yourselves. Okay. Now let's talk about our future work. Okay. Here, let me review the background to talk about future work. First, we focused on improving performance for CPU-based processing within the current execution model. Next, we will turn our attention to the overhead that occurs in data transfers between GPU tasks. There are two key points we are focusing on. The first point is the unnecessary data transfers by the CPU, which are not essential to the data processing itself. Currently, when GPU-based tasks are executed in sequence, the data must be routed into the GPU, then written back to memory, and again routed and written back repeatedly. This causes redundant data movement that doesn't contribute computation. In other words, CPU works unnecessary, which causes additional overhead. The second point is that, although data processing within each task becomes faster thanks to the accelerators, such as GPU, but the network speed has not been able to keep up with it. To improve performance, we are introducing a new technique called accelerator chaining in the processing pipeline. The names come from the idea that data is passed on between accelerators, forming a chain. Accelerator chaining is a technique that performs the following two functions. First, it leverages the most suitable accelerator for each task. So, what I mentioned in the introduction part was actually part of this technique. Second, it transfers data to the next device directly and quickly. Here's how the data flows. When GPU-based tasks are executed in sequence, the data is loaded into the GPU and then sent directly to the next GPU, using GPU direct RDMA. For this data transfer path, we plan to use a high-speed network through the second link. Now, let me share the current progress of the accelerator chaining work. At this stage, our goal is to enable communication between second links using fixed IP address. This approach is designed to support a new communication path, so it's separate from the one currently supported by Numaflow. And fixed IPs of second link is assigned by DRA. And we are planning to start discussion with the Numaflow community about introducing this new feature. In the future, to realize accelerator chaining, we would like to support IP address management and name resolution for second networks within Kubernetes. For this plan, we use a CNIDR driver, which is a reference implementation of multi-network subproject under the SHIP network. Let me briefly explain how it works. When a pod is created, its manifest includes a DRA field that contains the CNI configuration. This information is passed to Kubernetes, and the CNIDR driver, which runs as a Kubernetes plugin, and it detects the pod creation event and performs a CNI add operation. Through these processes, an IP address is assigned to the second link by IPAM. Before the data transfer begins, name resolution will be performed. As a result, users can now use accelerator chaining. Finally, let me summarize the second half from the demo. We have shown two demos. In the first demo, we update the accelerator through building a video inference system. In the second demo, we update the inference model through the integration with the ML lifecycle. And finally, for realizing accelerator chaining, we are planning to propose a new feature to Numaflow community and work on supporting the second network within Kubernetes. So before closing, I'd like to express my gratitude. Thank you very much for attending this session. Your feedback will be greatly appreciated. I'd also like to thank the open source community that are involved with our pod. And I look forward to your participation and collaboration. In addition, Intuit, which mainly leads the development of Numaflow, has a booth here, in Solution Showcase. Please stop by and take a look. Okay, thank you very much. That's all.